Okay.
Yes, please go ahead. Have a good session.
Okay. So hello everyone. Welcome to the session of post-quantum cryptography. This session has 3 papers, and each talk has 5 minutes, and followed by 5 minutes for Q&As. And I, Akinori Hosoyamada, and Andreas Helsing serve as the session chairs. And the first paper is Scalable Ciphertext Compression Techniques for Post-Quantum Games and Their Applications. The authors are Shuichi Katsumata, Chris Kowalski, Federico Piantore, and Thomas Prest. I'm sorry if my pronunciation is not good. And the speaker is Thomas Prest. Please start.
Thank you, Akinori, for the introduction. So the main question that you are concerned with in this talk is how efficiently can we share one session key between n+1 users? And at least one natural motivation for this question is secure messaging. So if you have n+1 people who wish to speak together, a simple way to do that is that they all share a symmetric key, and then they use this symmetric key to encrypt messages. But first, they have to share this symmetric key. And so a simple way to do that is to use public encryption. So for example, if we use El-Gamal, then one user will send n ciphertext to the n other users. Each ciphertext will have 2 group elements, and so the number of elements of group elements broadcast will be 2n. And in 2002, Kurosawa did a nice optimization, which is a nice observation, which is to observe that actually you can do some sort of mutualization, because in each ciphertext, the left element G2DR, you can use the same for all the recipients, and then it's only the second element that you're going to repeat for each recipient. And instead of sending 2n elements, you're going to send n+1 elements. So asymptotically, you save a factor 2. And this trick has been called, at least by Kurosawa, randomness reuse. The study of having this sort of group key agreement has been called multi-recipient PKE or multi-recipient KEM, or MPK and MKEM. And in this work, we will provide a simpler formalization of these techniques and what they provide, study their post-quantum security, and show some applications. And the core notion that we rely on is decomposability, and it's a very simple notion. Essentially, it states that if you have a ciphertext, which is an encryption of a message M under a public key PKI, then it can be decomposed in 2 parts. So the left part will be, as you can see, independent on the public key and the message, and only dependent on some random coins. And it's only the second part that's going to depend on the public key, the message, and again, some random coins. And if we look at the previous example of El-Gamal, then we can see that it's decomposable. So we take CT0, the left part, equal to G to DR, and the right part, CTI hat, is PKI to DR times M. And then we define, we put forward multi-PKE, multi-recipient PKE, where the ciphertext with n recipients will be CTRO, where you have the same CT0 for all the users, and then you only repeat the CTI hat. And then key generation and decryption remain the same. And this is interesting in a post-quantum world, because this applies to Lindner-Peikert schemes, such as Saber, Kyber, and so on, to the isogeny-based candidate Cyc, a NIST candidate for the standardization by NIST, and also to the scheme CSIDE. And regarding active security, we showed that if you have a decomposable NCPA MPKE, then we can obtain a NCCA MKEM in the QROM. And we rely on a decomposable generalization of the Fushizaki-Okamoto transform. And a pleasant surprise for us was that when we looked at the impact of this technique on post-quantum schemes, so remember that for El-Gamal, it provided a factor 2 in terms of efficiency gain. Well, for post-quantum schemes, we get at least, in the case of CSIDE, a factor 5 in terms of gain. And then for all the other schemes, we get even more impressive communication gains. And in the case of Frodochem, I think we gain more than 60 in terms of computation cost. And finally, we also show an optimization of TRIChem that is allowed by MKEM. So basically, the idea is to combine TRIChem and MKEM. So TRIChem is a sub-protocol of the MLS protocol for secure group messaging. And it's also the bottleneck of MLS because it's doing a lot of public key operations. And in TreeChem, users are going to be arranged as the leaves of a binary tree, and then a user refresh her key material by broadcasting one public key for each node in the path and one ciphertext for each node in the copath. And in our paper, what we propose is instead of using a binary tree, we use a MRE tree. And since all the ciphertext at the same level will encrypt the same key, then we can use MChem. And this allows us to have some gains. So for example, if we use that for Cyc, we can gain a factor 2.5 compared to the standard solution. And with Frodochem, we can gain a factor more than 4. And so this concludes my talk, and thank you for your attention.
Thank you, Thomas. Are there any questions? So please post them best in the Zoom chat. While there are no questions yet, maybe one question from my side. Is the reason for this massive improvement that the randomness size for post-quantum schemes is just a big bottleneck in general?
Sorry, can you repeat?
Is the reason that you get so good improvement numbers that the randomness in post-quantum schemes is a lot bigger than in other schemes, like in the conventional encryption schemes?
I guess that's a way of saying it, but what really enables our gain is that this randomness that you mentioned, it's all concentrated in some way in a part which is independent of the public key. And if it wasn't, then it would be harder to apply our techniques.
Do you think this also applies to, for example, code-based schemes, which you didn't look at? Or did you look at them?
We did look, we did notice that many code-based schemes, such as Bike, for example, they rely on the Lindner-Peikert framework, at least on a very abstract level. It's not the same name, but you see the constructions, they are the same, but with different metrics. So yes, it would apply, but we have to study the security implications. So it will rely on a variant of LPN instead of relying on LWE.
Nice, thanks. So are there any further questions? I think if not, then maybe questions can still be asked after the third talk. And Akinori, you want to take over?
Akinori, I apologize, you're muted.
I'm very sorry. Yeah. Can you hear me?
Yes.
Yes.
And so next, I'd like to move to the next paper. The title of the paper is Post-Quantum Verification of Fujisaki Okamoto. The author is Dominique Unruh, and the paper will be presented by Dominique Unruh. Please start.
And Dominique, you're also muted.
Okay, sorry. Yeah, the Zoom gets small when I share my screen and then I don't find it anymore. Okay, hello and welcome to my talk. So we'll talk about recent results on the post-quantum verification of the Fujisaki-Okamoto transform. So to start, let me say a very few words about the Fujisaki-Okamoto transform without any details, and this is a 5-minute talk. So the Fujisaki-Okamoto transform is a transformation for constructing public key encapsulation mechanisms in the random oracle model. So for those not sure about the difference between CAM and encryption, just think of it as public key encryption. And it takes something with weak security, for example, with chosen plaintext attack security, and makes CCA security out of it. And it's used in many, or probably even most, of the efficient post-quantum public key encryption schemes that are currently under discussion, such as the NIST post-quantum candidates. And in this talk, I will focus on one specific variant of it, proposed and proven by Hövelmans, Kills, Schäger, and Unruh, this year's PKC, which does, it's an Fujisaka-Komoto variant with support for decryption errors, which is very important for lattice crypto. Second part is formal verification. So what's that? Well, the standard approach when we do cryptography is that a human writes a security proof and a human reads the security proof. And this is unfortunately very error prone because especially with quantum crypto, its proofs are not very intuitive. It is easy to make proofs in the details. So an expert needs to check the whole proof from start to end. And the alternative is formal verification. So maybe still a human writes the proof. What we want is that a computer checks every proof step. Now we need experts to write every proof step still. But if you want to be sure that it's the right thing, an expert only needs to verify the specifications such as security definitions and so on, but not all the details of the proof. So this gives us much higher assurance. In the classical setting, there are a lot of approaches for formal verification already. Many tools exist. Most well known is probably EasyCrypt. And they all are based on the game-based proofs approach, where we have a sequence of games and show the relationship between two consecutive games. And how this consecutive game relationship is shown, that depends on the individual tool. Unfortunately, none of these previous tools are quantum sound. So, for example, for EasyCrypt, you can build a counterexample that is shown secure but not post-quantum, is not actually secure against quantum adversaries. Fortunately, there's a way out. There is the logic QRHL, quantum relational Hall logic. It's a logic to relate two games or two programs following the approach of EasyCrypt, and this logic allows us also then to do game-based proofs. There's a theorem prover for this, but so far this theorem prover QHL tool has only been used for toy examples. So we don't know, does it really work for big crypto proofs or not? And this is our contribution in this work. So we formalized the security proof from HKSU for the Fujisaka-Komoto transform. This is the first non-trivial post-quantum security proof. It's especially tricky because it does involve the quantum random oracle model. So it's not a proof that where every step is kind of classical. And this makes it particularly interesting as a case study also, besides its own relevance. It shows that the using QHL for doing post-quantum crypto proofs is viable and hopefully can be used for many more other interesting protocols. We also extended the tool by adding support for the one-way to hiding theorem, in case you know what it is, and showed also the need for some other extensions of the language. I'll skip this because I'm out of time. And I thank you for your attention. And here's a little advertisement for anyone interested. Thank you.
Thank you, Dominic, for the nice talk. Are there any questions? So far, I don't see any in the stream. Did you start looking also into other protocols yet, or is this all in submission and so you cannot talk about?
I did not yet look into other protocols, but I certainly plan to do so. So I think one important thing would be to look also at the other NIST, at the NIST candidates, for example. This is Fujisaka-Komoto, which is used, but I think to have high assurance, one should look at the NIST candidates exactly as they are proposed, and also look at the signatures and so on. So there's a lot of interesting work there, and then also actual quantum protocols like key distribution. So a lot of future work, and I'm excited about doing it.
Yeah. So another question that pops up for me is, for this formal verification, what often happens is that you get more and more facts that you essentially put in there, which you actually have to be verified by humans. Right? You have to make certain statements that you do not really prove from the basic, but
I'm not sure what you mean. Can you give an example? Just to know what kind of facts you mean. I mean, can even be a silly example. I just don't understand what you mean by facts.
That a certain numbers, for example, uniformly distributed and independent of all other variables.
Mm-hmm.
How many of these kind of statements do you actually have in your proof?
I don't really have any such assumptions. I mean, other than what follows from how I write my security game. I mean, it's the same as in the handwritten proof. If I say something like K is sampled from this distribution in the game, then it will, of course, be independent. But I don't make any assumptions that are outside the security definition. One technical distinction, one thing that I technically assume more than I would in a pen and paper proof is about the complexity of the adversary, like the query number, because I had to state like 20 or 30 axioms about that. But basically they were all like, with this oracle, you do this many query, with this oracle, you also do Q queries and so on. So this is still a technical limitation, but not a principal one. So basically you shouldn't have any assumptions that you don't have in a pen and paper proof.
Okay. There's one question on the chat from a name in Japanese, Chinese characters. I don't know. So I don't know the name. But the question is, what is the main difficulty in formal verification from classical to quantum?
Mm-hmm. So there are three things which I encountered in this specific proof. One is that you sometimes, that you always need to talk about the adversary state, and this adversary state can be quantum, and you need to talk about the adversary state being somehow equal between two consecutive games, which most of the time is something you just drag through your proof, but sometimes it leads to unexpected consequences that, for example, you can't just say, okay, no, this variable is not used anymore, we just drop it. Somehow, because it's entangled, you get into trouble. So a lot of things you need to be more careful. And the second thing is that sometimes you need to reason about actual quantum things. So in this protocol, we had that you have a function h that is defined as roughly the composition of two other functions, a bit more complicated. And this is a kind of trivial operation. Even if you want to give superposition access to it, you need to compute one, then the other, uncompute one. But actually proving these things is kind of tedious. So this makes the difference. But I would say that 95% of the work is just the same as you would do classically, with then the occasional proof step where you need to think about quantum things.
Okay, thanks. I think we're a bit out of time. So if there are further questions, you can ask them in the chat, or maybe at the end if we've got time left. And then we should move on to the next talk. Thank you.
It's like, thank you to Dominic. And I'd like to move to the next talk. And the next paper is a new decryption failure attack against HQC. The authors are Django, Thomas Johansson, and Django will give a talk. Please start.
Hi, thank you for the introduction, and thank you. Welcome to my talk. So I will talk about a new decryption failure attack against HQC. So HQC is short for Hamming quasi-cyclic. It belongs to code-based crypto, and so HQC is a submission to the NIST PQC standardization project. It has advanced to round 3 and in the category of alternate candidates. So NIST commented on HQC that HQC presents a strong argument that its decryption failure rate is low enough to obtain chosen ciphertext security. this is the strongest argument at present of CCE security among the second round candidates code-based crypto system. Here, our main focus is a new key recovery chosen ciphertext attack on HQC, and we will target round 2 parameters in the NIST PQC project. So this is the HQC scheme. So we start with in the CPA PKE, and then we achieve in the CCA2 CAM through a variant of the FO transform. Note that no multi-target protection is implemented in HQC. So we need to know how the HQC decryption failure will occur. For error correction, HQC use tensor product code. So it's a tensor of this BCH code and the repetition code. If we have this length n1 times n2 code word in vector, so we see that we have n1 repetition decoding chunks, and each of size this. If we have in one chunk, if we have this many position errors, then we will have a repetition decoding error. And if we have this many repetition decoding error, we will trigger a final decryption error. And this is the final error term. So our attack model, we adopt the wiki decryption failure attack model published at PKC 2019, but here no wiki key is assumed. First, we pre-compute weak ciphertext. So we just construct a set of weak ciphertexts which are very likely to introduce decryption errors. Then we submit this chosen ciphertext for decryption, and we collected the errors, decryption failures, and then we do statistical analysis on the collected errors to recover the partial key information. Last, we may also introduce, include a post-processing step here, because here it is a code-based crypto, so we will use information set decoding. Now we introduce basic ideas. We need to increase DFR. So if we only look at this x times R2 part, so if we assume that R2 is a random vector of fixed weight, we see that this will spread uniformly over this vector. But if we choose R2 as a vector containing an interval of many ones in this chunk, so then we see that there will be, for instance, this repetition decoding chunk will have many ones here, then the error probability will be higher. Next, we want to connect the partial key with this collected errors. Here we see that because X is very sparse and we know this R2 means that if here we have Xi is 1, then we see that the corresponding repetition decoding interval will have many ones here. So otherwise, if we detect that such an interval occurs, we will predict that, okay, with a good probability that the corresponding Xi could be 1. So the problem is to distinguish if such an interval occurs. How to do that? Here we denote, we have two types of intervals, one including this chunk. This is case 1 interval, this is case 2 interval. We don't have this chunk. So we know that the tuple R1, R2E is known, and also the noise can be represented in this form. The main observation is that independent noise part E is helping out to make the decoding error. So if we look at this probability that EJ is 1, EJ is the J's position of this E. So if we look at this property conditioned on errors, so we see that for the case 2 interval, because this repetition decoding will be correct with high probability, so these two are not correlated. We have a p-random. But for this part, we know that there's many ones here, so means that the probability to be honest is high, so means that EJ with high probability will be 1, means that because this is sparse, we know that this plus this will be high probability to be 1. So it means that if we denote the contribution from this part to be epsilon part, so if this is 0, then with high probability, this one will be 1. Otherwise, if this is 1, then with high probability, this one will be 0, with a relatively high probability. So we have P high, P low. Then we use this property to distinguish. So The conclusion is that we're concluding our results. We present a novel CC attack while exploiting decryption failures. We present a successful attack on HQC 256.1 in the NIST setting. And for these 3 parameters sets, they are all affected in different attack models. For instance, if we assume that the pre-computation is free or the pre-computation can be amortized. For these 2 parameter sets, they are still safe. So to protect against this attack, we suggest to remove this parameter set, and we suggest to include the multi-target protection. And finally, note that this is not a weak key attack, so it is an interesting problem to study the weak key behavior of HQC. Thank you very much.
Thank you for the talk. There's a first question that asks, you use ISD in your pre-computation stage, right? ISDs for decoding unstructural random linear codes, but your decoding seems to have special form. So does the complexity still work?
We use SD in the post-processing step. This means that from this decryption failure, we can treat it, get some partial information, but we cannot fully recover the key. So this is like easier ISD problem. And here we just use plain ISD, the simplest form, like Prange. But definitely, if we include the stronger ISD, we will have a stronger result, maybe slightly stronger.
Thank you. So far, there are no further questions. Maybe one from my side. Can you put the finger on why this works for HQC and, for example, not for bike? Or does it maybe work for bike? Like, what's the problem?
I think, I mean, for bike, it's hard to say, but for bike, it's difficult to have like a very accurate prediction for the error decryption failure rate.
So the statement would be that because you have you can predict the decryption failure rate well.
I mean, for iterative decoding, you need to. I think it could work. I mean, similarly, but the thing is, for bike, you need to have simulation to simulate this, or maybe this theoretical prediction is not accurate enough to have convincing arguments. Like,
okay.
Also, I guess this weak key behavior of bike could be very complicated.
I see. Thank you. There's one more question by Yang Jun. Can this attack be combined with weak key attacks?
Yes, we guess so. Could be, maybe, but I think we may improve something, but yeah, is it a huge like a huge difference? I don't know. If there will be a huge difference, but it could at least lead to some minor improvement, I would say.
Okay. Thank you. There's one last question that was asked for Thomas. Maybe if Thomas is still there.
Yes.
And that was, there was a recent result by Alvin et al. Presented at Crypto 2020 showing that TreeCam was not forward secure. Does this also apply to your construction, or do you solve this problem?
Sorry, I'm.
Yes. So,
sorry, I'm not familiar with this result.
No, this is for Thomas. So sorry, that's for the first paper. So that was just came up during the.
Okay, yes, this is an interesting one. So in the paper by Alwen et al., they show that the generic construction of TreeCam, which is the one that we base ourselves on, is not forward secure. So the proposal that we have in our paper is not forward secure either. And the solution that they propose is to use an update table PKE. And That's also very interesting because as far as I know, it's an open question, an important open question to build updatable PKE from lattices. And at the moment, it's not solved. So unfortunately, our construction is not forward secure in that sense. But something I would be interested in is if someone comes up with a lattice-based updatable PKE, will it also be compatible with our construction, with the optimization that we provide? And I'm talking about lattices because this is what I know the best, but the same question applies for isogenies.
Thank you. I think we are perfectly in time.